problem on the connection, so I will take my video off just to avoid any interruption during our discussion. Okay?
No problem, Professor.
Okay, so we can start. And we were discussing about PM techniques, and we left last time with the necessity to have powders, which must then be consolidated in order to fabricate the final component. And one way, one possibility to have powders also in the form of alloyed powders, we already have seen, is the use of mechanical milling and eventually mechanical alloying techniques by using a mill. Other two most very important technologies which broadened the possibility to fabricate metallic alloys in form of powders to be used as raw materials for PM techniques are, we already mentioned it, the water atomization and the gas atomization. What is the water atomization? It's the most widely used technique essentially for producing iron-based and copper-based powders, and it has also replaced in the last years other technologies like thermochemical or I would say electrolytic processes, because it is characterized by lower cost and more higher flexibility. In this case, we do start by a liquid metallic melt. The melt is obtained by using a furnace and then is ejected through a nozzle, and the same melt stream is then fragmented by an interaction with high pressure, as in the skin, water jets, which are able to generate a broad granulometric distribution of the solidified powders. In this case, we do have a very high, significant high cooling rate due to the interaction between the melt and the water stream. And this cooling rate is on the order of 10 to 5 Celsius per second. Due to the fact that this is a very high cooling rate, usually the fabricated powders, they do not have sufficient time to become spheres, and so they usually generate an irregular shape. This is something positive if we think to the further step related to the fabrication of a green body by pressing. And there is also another important things to be considered due to this high cooling rate, that essentially, if we talk about iron-based powders, but in any case, metals, we can react with oxygen, that this very short time which is requested to solidify powders allow to reduce the oxidation of the powders itself. And so, generally speaking, for iron-based powders, the oxygen content after solidification is quite low, typically around 1% in weight. If we start from a melt, but we are not establishing an interaction with water, instead, we are going to establish an interaction with air or with an inert gas. We do have the gas atomization techniques. This is usually used for low melting metals, or also for very reactive metals, obviously in this case without air, but by using an inert gas, such as, for example, aluminum and titanium, or generally, since it can operate in an atmosphere where oxygen is not present at all if we use an inert gas, every time we require a very high purity of the powders fabricated after solidification, such is in the case of nickel-based superalloys or HSS, which means high-strength steel. In this case, the metal stream is going to interact with a high-pressure gas stream, and so also in this case, particles with a very wide granulometric distributions are formed. But if we want to compare this technique with the other one, with the previous one, that is with the water atomization, in this case we do have cooling rates which are 2 orders of magnitude lower than water atomization. That is more or less around 10 to 3 Celsius per second. And this, let me say, in terms of comparison, high cooling time, which is necessary to solidify, so higher solidification time allows to the powder itself to form spheres. So spheroidization is possible. And this shape, in terms of sphere, even though it can, let me say, represent some small drawbacks when we look to densification for the green body formation, but led the powders to be best flowing inside any dyes. And this is, let me say, an advantage if we use spheres as powders, because they have higher, better, good flowability, and so we can ensure a high packing density. After powder fabrication, we need to press, and the first step, as we said, is to form a green compact, where in some cases, we can use also some binders, and pressing usually is performed in rigid steel dies, and according to the compaction pressure, here you have some data which refer to iron powders, but the concept is generally applicable. If we increase the compact pressure, we can increase the green density of the green compact. We are not able to reach the theoretical density. That is, we are not able to eliminate all voids independently by the shape, initial shape, fragmented of spheres of the powders. But in any case, the density is going to be increased with the increasing of the pressure which is applied inside the dies. This residual porosity, which still stands in the green compact, needs to, for us, it requires to us to use, as we will see later, also the sintering step when we want to develop a 3D fully dense or very, very near to fully dense materials. In order to lower the final residual porosity, which for structural applications represent a problem, it is not a problem if we are thinking about application, as I showed to you last time, where, for example, solid lubricant can be inserted inside the porosity. But if we are talking about components to be fabricated after sintering, for structural application, that is, components which must withstand with general applied loads, mechanical loads, thermal loads, and so on, porosity represents defects. And we know and we remember that the amount of defect, just think again to the design approach based on the damage tolerance approach, which is going to be defined by the fracture mechanic approach. In this case, porosity is a drawback for the material. Densification by compaction rather than sintering has the main advantage of preserving in any way dimensional precision, because it lowers the shrinkage which is achieved during the sintering step. This means that if we are going to use as a pre-sintering or pre-sintered materials a green compact having a higher value of density, that is a lower value of porosity, we can expect lower shrinkage phenomena, which affect obviously the final shape and size of the component. But this is not made without any cost. That is, if we have to apply pressure before sintering, this is, as it usually happens, an additional step into the fabrication route, which give rise to additional cost. But in any case, for the materials which are interesting for us, for our application, since we need to eliminate most, all, I would say, of the porosity in the green compact, we need to apply suitable pressures. And when we make these, we can also reduce the shrinkage secondary effect by having then, after sintering, a final component with proper and with suitable properties for the engineering application. On pressing, there are some arguments which are not, let me say, are specialist arguments, but just to mention to you, which are not so important for us. Obviously, we are going to press inside the die, so that many research have been done in order to find efficient lubrications, just to reduce, for example, the dies wear, and just to have a more uniform distribution of pressure, that is the same degree of pre-compacting inside the wall mass of the component, which will then be sintered. And then after this step of preforming of the fabrication of the green compact, and remember, this is the same terminology that we use for the ceramic materials, even though we are talking now about metallic alloys, we must let sintering to happen. Sintering is a spontaneous process which is driven by the free energy reduction that the power compact can achieve by lowering its exposed surface. And as we said, this is a process which is essentially driven by temperature and by solid state diffusion, even though we do have some variance. In this picture that you see on this slide, you have the first one, which is the green compact, and you see the amount of black areas, which are essentially voids between pre-compacted particles. And after, in this case, just 15 minutes, so this is not an optimal time for this alloy, but in any way, you can see how the black area are going to be reduced due to the fact that solid state diffusion is able to enable mass transportation, thus recovering the initial voids. And this is also the case because the reasons because of, you can expect also shrinkage after final compaction and final sintering. Many factors can affect the sintering behavior of a powder, so pure powders or alloyed powders, the powder reactivity, the degree of compaction, as we said, and obviously temperature and time of the process, and the application during sintering. This is not mandatory, but usually is done because the production time cycle so can be shortened. The use of an external applied pressure during sintering, that is, we are going to establish not only a thermal treatment, but a thermomechanical treatment, as well as, according to the powder reactivity, the process atmosphere, which must be controlled when, for example, we do have powders which are very prone to be oxidized, that is, powders which are very prone to react with oxygen, and we want to minimize oxides after final compaction and sintering of our component. The powder reactivity is determined by the surface which is available. And if you remember what we said when we talk about the nano powders, obviously the surface to volume ratio is related to particle size, and in this case also to particle shape. And in order to, let me say, define the best and the suitable processing parameters for taking into account powder reactivity, which is a processing parameter controlling sintering phenomena, usually it is referred to the specific surface of the powders. And if we have a higher compaction degree, that is a green body with an higher density, the reactive surface will be lower, and thus also the sintering activity will be lower. But this means that we can get the final results by reducing, let me say, the kinetics of sintering, but at the same time having the positive effect, as we told before, of reduction of the drawbacks due to the shrinkage in the final component. Sometime, in order to speed up and to have a more efficient sintering process step, master alloys are added to the powders, and this is made to reach higher value of sintering degree without essentially make big alteration of the overall powder composition or granulometry. And this master alloy, which is used, in some cases, that depends on the composition, obviously, can also give rise to liquid phase, very reduced in terms of amount of liquid phase, which are around the solid powders, initial powders, and which can, let me say, speed up the sintering. And in this case, we say that there is a liquid phase sintering process. But usually, and generally speaking, the sintering approach does not involve any liquid phase, at least of the starting materials, not of the master alloys, being obviously, and again, I say, based on solid state diffusion process. This process, if you remember diffusion, solid state diffusion, just let us to recall it. Solid state diffusion, it is governed by two laws, the so-called Fick law, which can be classified, there are two, according to the steady state or unsteady state situation. But in both cases, in the first one, when we do have a steady state, we do have concentration which is not varying with time. In the non-steady state situation, we do have concentration which is instead varied also with time. That's the difference. But in both cases, we do have inside the very simple formula of the monodimensional Fick law, the diffusion coefficient. And if you remember the diffusion coefficient, it has an expression like an Arrhenius law, and it has inside, apart the Nepero number, the temperature. And how high is the temperature? So high is the value of the diffusion coefficient. So high is the diffusion phenomena. So since we rely on solid state diffusion in order to recover voids, and we cannot wait, let me say years, but we are discussing about technologies, production technologies, which must be compatible with engineering time for fabrication of components. Generally speaking, then again, each kind of materials has its own range or optimal temperature value. We are talking about processes in which the temperature requested in order to develop solid state diffusion for sintering are higher than 1000 Celsius. They usually are in the range 1100, 1200 Celsius. And this can, let me say, limit the time which is necessary to obtain the final structure, that is to complete the sintering step in time which are essentially reasonable because they are near 30 minutes, half an hour. So this just to remember, and then obviously I say every material has its own properties, but if we look to the melting temperature of iron or iron alloys, to the melting temperature of nickel-based superalloys, for example, we do not have so much difference. We need to involve in our fabrication step a phase in which high temperature is involved, just to let the diffusion coefficient high enough to have mass transportation in reasonable engineering time for fabrication of the components that we want with our starting powders. The atmosphere of sintering is important, again, as I said before, but I want to underline again, depending also on the starting materials composition, because in any case, the sintering atmosphere must preserve the densification without formation of unwanted compounds, like, for example, oxides. And so we can have a situation in which, as well as in the gas atomization, we need to carry out our sintering step in protective or inert atmospheres in order to avoid that oxygen, for example, can react with iron, or could react with titanium, or could react with aluminium or with nickel. So most of time, especially for reactive species, with regards to the possibility of affinity with oxygen, we need to make our sintering step in a protective atmospheres for the alloy we are going, for the materials or the alloy we are going to consolidate. After sintering, So we have got our final component in a net shape, and we need to design where, depending on the pre-compaction pressure that is used for the green body, also we need to design also the expected shrinkage, because our final component is that obtained after sintering, not as a green compact. We can have also secondary treatments, which usually do not involve mass subtraction. I mean, being the final component net shape, we can have finishing of the surface by polishing, for example, in order to, where it is necessary, to lower the roughness of the fabricated component, but no more than this. And in some cases, we can have thermal treatments, or in some cases, we can have also a two-step sintering that depends on the starting materials. Which are the powders which are most produced to be used for power metallurgy techniques? In terms of quantity, as you see from this graph, even though it's not updated to now, but the relative quantity have not been modified, essentially you see that the most important in terms of quantity is iron, and so not pure iron, I mean iron alloys, whilst the alloys for high temperature applications in our field, like nickel-based or cobalt-based superalloys, or in some cases titanium, you can see from this graph they are very, very minimal, as I told to you at the beginning when we were talking about, let me say, the possibility to fabricate components for our purposes by using powders. So iron-based alloys and also iron-based superalloys in terms of quantity are the most produced materials worldwide to be used for power metallurgy techniques. But if we see, not in terms of quantity, but in terms of value, what we can see from this graph, that this technology is very, very important, is the most important technology for the fabrication of neodymium iron boron alloys, which are essentially materials used for magnet, so for magnetic materials. Then, following this, there are again the iron-based superalloys and also ceramic metal materials like tungsten carbide, cobalt, which are used for wear-resistant purposes. Here you have some, let me say, graph in which you see where powder metallurgy is used. As I told to you, as you can see here, around 80% of European power metallurgy production is made by using iron-based alloys, and more or less 70% of components are for application in automotive sectors, which is actually the most important application market for the overall powder metallurgy sector. Here you have some example of components which can be fabricated by using iron-based materials in the automotive fields. But we do have also others, even though they are niche application, but interesting, by using the possibility to control, as we told, the final porosity, because if our aim is to eliminate completely the porosity, we can make our sintering step up to a stage for which the solid state diffusion is able to eliminate the porosity in the green, compact. But we could also decide to fabricate porous materials. In this case, our sintering step will not be made up to the end, but it will be stopped before. And this is the case in which we are going to use, for example, again with iron, but essentially iron, copper, or bronze and graphite additions, bearings in which the final porosity, which is designed for the fabricated components, is not 0 point something, but is quite high, from 10 to 35%, because this porosity becomes a lubricant reservoir after impregnation under vacuum. And so having dry lubrication properties of the fabricated bearings. Hard metals, we mentioned before, tungsten, carbide, cobalt, they are also fabricated by powder metallurgy. Essentially, this is the most used, let me say, combination. It's a ceramic metal matrix materials with a cobalt matrix to 25% in weight, and then we're having dispersion of carbides at essentially tungsten carbide. In this case, we use usually ball milling, and then after, in order to have alloyed tungsten carbide cobalt powders, and then powder metallurgy with sintering. You see here the temperature, the sintering temperature are higher than those I mentioned before, because we do have, in this case, a ceramic phase inside, and they are used, these hard metals, powders, and final components for application in which we do need a good, for example, wear-resistant properties on the surface for the fabricated components. And here you have some examples, and depending on the, let me say, components, we can vary the percent as well as the granulometry of the ceramic phase, that is of the carbides. For example, we can have very, very small grains, submicron, essentially submicron, sometimes nano, but essentially they are submicrons, the ultra-fine grained, for example, for micro drills, up to mining tools in which we do have the metallic matrix, the cobalt one, which is able to ingolate, that is to have inside tungsten carbide particles to an extent which is something around 15% in weight, but with average size which are in the micron range and not in the submicron range. And this is also, let me say, even though it's a very specialized field, a field that we could say, generally speaking, of the cutting tools, in which insert or components are made by using ceramic metal materials through powder metallurgy technologies. Also diamond tools, which are composite materials made of a metallic matrix that is a binder with 10 to 5% in volume of industrial diamond dispersions. They are fabricated by powder metallurgy technologies. They usually imply the hot pressing techniques together with free sintering of the materials itself. And this is one example. And also in this case, diamond tools usually they have as main application fields the area of the cutting tools for materials machining in a laboratory and in industry and engineering level. Some other example of this possibility. And magnetic parts, as I told to you, they are very, very important for this kind of fabrication technology. We can have hard magnet as those which are based, and they are the most performing because they can give to us high coercitivity and high residual magnetization with high hysteresis loss. And here you have a list. The most performing up to now at industrial level, I would say, not at lab level, are those based on the powders that we mentioned before, that is the neodymium, iron, and boron. We can have also soft magnets, which display higher permeability, low coercitivity, and so lower hysteresis losses. And these are used essentially in electric motors or inductors cores or sensors, and are essentially made by iron base, sometimes modified with silicon, nickel, phosphorus, but iron-based materials. Also, these small parts are widely fabricated by using powder metallurgy techniques. Okay. And another application of powder metallurgy, which must be mentioned in order to complete our panorama together with the last topic that we will discuss in a few minutes, is the so-called MIM technology, which stands for metal injection molding. This is a manufacturing process characterized by the fact that metal powders is combined with a binder. More or less the amount in volume of the binder is around 50% in volume. Is then this metal powder is granulated and it is injected into a die. The green part, so, is debinded by dissolution or by a chemical or thermal decomposition. Thus obtain, this is the, let me say, technical way to call it, the so-called brown part. So we start from green and we get a brown part, which still has inside a small fraction of binder, holding together the original powders. Then we do have the sintering, and this sintering step is able to reach up to 95 to 99% of the theoretical density with a strong shrinkage, you see here, because yes, essentially we do not have pre-compacting as we have shown before, and so the shrinkage can reach values up to 20%, and this must be taken into account for the design of the fabrication cycle, because again, what we have as the final component is what is going to be fabricated after the sintering, step. Metal injection molding is usually used as fabrication technology for big volumes, for big series of small parts, and most important materials which are used for these techniques are steel, essentially low alloy steels or stainless steel, for automotive application and for some other consumer goods. Here you have some examples. For example, the watch case made by stainless steel is made by MIM. There are also other applications like those based on titanium alloys. Here it is mentioned that the titanium 6% aluminum, 4% vanadium, which is a biocompatible material. So it can be used, and it is used for biomedical component, but at an overall let me say, look again, as in the powder metallurgy, generally speaking, as we have said before, iron-based, that is stainless steel or alloy steel, for automotive sector are the driving market for this kind of technology. The possibility that we mentioned to make at the same time during the sintering the application of both temperature and pressure give rise to the so-called hot isostatic pressing. This is just to recall to you, because we already started this kind of technology when we have discussed some time ago, some years ago, about fabrication technology for ceramic materials, in which hot isostatic pressing is the leading techniques for the fabrication of bulk ceramic part, starting from powders and then consolidating these powders up to the green body by sintering, in which a thermomechanical cycle is applied. So we are going to apply at the same time high pressure, and there are very significant value of pressure which are higher than 100 megapascal. So you can convert it in bar if you want, with temperature which are again in the range of 1,200, 1,300, 1,100 Celsius, depending on the starting materials in terms of materials composition and in terms of shape and size of starting powders. These techniques is usually used for the fabrication of small parts, also in this case, because we need a die in which we must apply an isostatic pressure, but components, even though they in volumes they are not so much, but in value for niche application they cannot be neglected, are found in energy generation components, oil and gas industry, some aerospace, military, nuclear, and process industry, and tooling. And the last, let me say, how to say, we would say class of techniques which belong to the powder metallurgy techniques, which we must mention, are those which are defined as AM techniques, that is additive manufacturing techniques. These are very, very interesting techniques due to the fact that they can offer a number of advantages, also in terms of material saving, as well as in terms of time of production, shorter than the other one. And they have received increasing attention in the last years. Even though there are still some drawbacks which make these technologies of the additive manufacturing very interesting, also in this case, and especially I would say in this case for the aerospace fields, some issues are still under study, are unapplied, not on a lab scale, unapplied research and development, let me say, activity. And one of the main issues which must be, let me say, considered is the actual availability of powders to be used successfully with AM techniques. I mean, we do not have still all the possibility of metallic alloys in forms of powders to be used with additive manufacturing technologies. So many research on powders and materials development are on the field. They are also called, even because they can be used not only for metallic alloys such as we are going to discuss now, but also for non-metallic materials, including polymeric-based materials. They are also, let me say, called as 3D, three-dimensional printing technique. And essentially, under the head of additive manufacturing technology, we include those technology which involve the fabrication, that is the building of a component of an object, starting from a three-dimensional model data by progressive joining of materials. And depending on the way in which these materials is added, we can have different sub-techniques belonging to the area of the additive manufacturing technology. Obviously, in this case, we add materials, for example, layer by layer, in order to fabricate our final component. And this is the opposite concept, the opposite approach with respect to the subtractive technologies, like, for example, machining. The most common, one of the most common, I will correct myself, one of the most common process in this area is the so-called selective laser melting. In SLM technique, each successive layer of metallic powder is locally melted by a laser, and so the object is built up by adding slices. So slice after slice, each slice more or less has a thickness of ranging from 20 to 100 microns. If we do not use a laser to melt the powders and then let them solidify layer by layer, but we use an electron beam, the ABM, electron beam melting technique, is defined. It is conceptually more or less the same thing, analogous to the SLM techniques, but we are going to replace the laser beam with an electron beam. There is also the third big area, which is the laser metal deposition, LMD, in which instead powdered metal is directly deposited under a laser beam, which is mounted on a multi-axis arc in order to reproduce the 6th degree of freedom and fabricate also component with a complex structure. Typical application of additive manufacturing technologies are, let me say, up to now, apart some special cases, can be found in biomedical area, in jewelry area, biomedical, for example, for dental components, but they have, let me say, received great attention in lightweight parts for aerospace application, as well as lightweight parts for automotive, essentially for racing applications. Most common materials available now are steels, stainless steels, titanium, aluminum, nickel-based alloys, but still, as I told to you before, more, let me say, work to develop suitable powders is to be made if we want to compare the possibility to have components made by this technique with a traditional, for example, casting technology. We do have also a standard definition by ISO for the additive fabrication, in which very simply is said that additive fabrication technologies are manufacturing processes which employ an additive technique whereby successive layers or units are built up to form a model, that is to form a three-dimensional structure, that is our component. And the history, let me say, to match the nowadays additive manufacturing technologies available starts some years ago, and we do have also some other definitions which have been then evolved in additive manufacturing. So we started some years ago in the 80s to talk about desktop manufacturing, then rapid prototyping, then rapid tooling, then three-dimensional printing, then free-form fabrication, and now we talk about additive manufacturing, which is the most recent term applied and used to describe this kind of technology. Here you have the phases of an additive manufacturing process in which we start from a conceptual development, and then we have, with all the subsection, the three-dimensional computer-aided design application, that is the design of the components, so the generation of the code of the file, which can control the manufacturing steps. For example, this means they can control the laser beam by a robot, by motorized arms, in order to fabricate the components that we want. And after that, we need to make some cleaning and processing on the fabricated component. We'll show to you in 5 minutes also video, so perhaps it could be a little bit more clear. I have reported to you, just for your knowledge and for your curiosity, the most important techniques which belongs to the AM area, starting from stereolithography, which is essentially, as you can see here by the drawings, refer to the fabrication of polymeric-based materials, moving to selective laser sintering or melting, that's the same, more or less, as the second possibility, to diffuse deposition modeling, in which we can use not only powders but also wires for fabrication of components, three-dimensional printing, so you have the most important, let me say, features of this basic technology belonging to the additive manufacturing technologies. The SLD, selective deposition or lamination. Then we have also some other technologies which are related to polymeric-based materials, like as resin injection and assisted by ultraviolet light photopolymerization of materials itself. And here you have a classification matrix of the process for what it concerns the general approach on the additive manufacturing technologies. You see here by sector, the most important are consumer products, motor vehicles, but we do have also some application on aerospace, and you have here some examples of components which are fabricated by additive manufacturing. While we are talking about additive manufacturing, don't forget, because we are starting again from powders, but we are going to make solidification, then the fabrication of our final component by solidification layer by layer, for example, and this belongs to the AM techniques. It opens many degree of freedoms for the designer. It is this technology connected, let me say, online. I mean, we do control the manufacturing process by generating a computer-aided design file, so with a computer-aided design approach. So it fully can be classified as one of the technologies belonging to the so-called fourth industrial revolution, which has been called initially in Europe a couple of years ago Industry 4.0. Now it is named Transition 4.0. And so additive manufacturing are very important because they can allow, due to the intrinsic properties, the possibility to be in line with the development of the digital fabrication technology. There are still some things which must be solved so that the application is not so very wide, as I told to you. For example, finishing of the surface, it depends on the technology which is used, can be a problem sometimes, depending on the materials, depending on the technology of the subclass that I mentioned to you used. We can have extremely rough surfaces, which is not a good thing for many structural applications, or since we need again to start from solid powders and then melt powders and then join powders, another thing apart from materials availability that I already mentioned to you is the strictly control of porosity of the fabricated component, which can affect, as we said at the beginning again today, in a negative way, the mechanical performance or the mechanical properties, or if you want, the life of the fabricated component. But nevertheless, it's a very important technology. Now many high specialized industries are buying and using for niche applications equipments which allow to fabricate small components by additive manufacturing, and there is worldwide a very big attention on this class of technologies due to also the fact that we can build up our component by a bed of powders, and the powders which are not used for the fabrication of the component itself, that is powders which are not melted and so not used to form the single layer or all the layer, can be also reused. We do have some safety problem with which we have to deal, because many metallic powders, when they are small in diameter, and for small diameter I mean in this sense something which is around 20 to 40 microns, they can be explosive, so they can be treated. They must be treated with a great attention in order to avoid security problem during the fabrication techniques. Many filters must be put inside the environment in which the additive technology is going to be used, even because this must be necessary to prevent health problem for the operators. But nevertheless, this is a very important and promising technology which must be monitored now, today, and also for the next years. Now let's just see together a small video which concludes the AM which we're talking about before starting a new topic in our discussion. Okay.
Metal Additive Manufacturing Technology Center, MAMTech, is the 3D metal printing research center in the Netherlands. We support companies from various industries in applying metal additive manufacturing. This manufacturing technology is used to fabricate metal products with less weight, better performance, and higher efficiency. MAMTech was established in 2013, starting with laser powder bed fusion, which allows the production of a wide range of alloys such as aluminium, titanium, and nickel-based superalloys. This is done by applying thin powder layers and locally melt the powder using a laser beam. Royal NLR is world-leading in...
Sorry, I was just to... You see here?
Royal NLR is...
You see here? That's the bed of powders from which the final component has been fabricated by using, in this case specifically, a laser head, and the remaining powders can be used, recycled, and reused for the fabrication of other components. For this, somebody says that this technology is also a sort of sustainable technology because it reduces the scraps, and the meaning is related to the main technical features of the additive.
Leading in 3D printing magnesium with laser-based powder bed fusion. In 2020, we expanded our facility with 2 new processes. First, the blown powder directed energy deposition, which uses a laser to melt powder which is deposited through a nozzle. This process can be used to manufacture parts, add features on existing products, or carry out repairs. Secondly, the sinter-based fused filament fabrication, which uses metal-filled polymer filaments for 3D printing. The printed parts are debinded and sintered afterwards. This is a fast 24-hour process to produce parts up to 150 millimeters cubed. The system is owned by the Dutch Ministry of Defence and is available to all armed forces, Royal NLR and TNO. Are you interested in our wide range of printing capabilities? Don't hesitate to contact us.
Okay, that one was just one example. I don't want to again to make any advertisement, but you have seen, let me say, with your eyes how by starting from a bed of powders we can, by melting and adding layer by layer, to reach the fabrication of a final component, which is the general concept of additive manufacturing. With this, we have concluded our discussion about powders, let me say powders metallurgy, so you have also an idea of the most important technologies which can be used for the fabrication of bulk components. And we start now another topic, so let me change my presentation, which is another class, I would say, of, as we said when we were discussing about the intermetallics and ODS, not conventional materials, even though in this case the possibility to mate this application is these materials is sensibly higher than the previous one, and it is the class of the cellular solids. So I want to discuss with you, first of all, what is a cellular solid, and which structure can we find inside the cellular solids, properties of these solids, and why that is application they can be interesting for us. And they can have a broad range of application because they can be made by using metallic alloys or polymeric alloys like foams, for example, or to some extent with some difficulties, but there are also examples of ceramic-based cellular solids, and but they do have also application in the aerospace fields. And so before going inside the description and some elements of the theory of the cellular solids, also in this case, let's have a look to this video, which is specifically made by Boeing, so you can, let me say, see with your eyes something that we will discuss with some formula later on. So let's start.
We were able to make the world's lightest material. The entire structure was basically 99.99% air. A microlattice is a 3D open cellular polymer structure and can often be compared to something like a bone structure. In your bone structures, the outside of your bone is very rigid, but on the inside, it's actually mostly hollow, where you basically have an open cellular structure, so they aren't easily crushed, yet lightweight at the same time. If you want to look at just properties in general, then one would be compression in the sense of energy absorption, and then the second would be lightweight in terms of having very hollow tubes. So let's say you have the egg drop challenge that a lot of students have in school, and they need to drop an egg from 25 stories and protect that egg. They would probably wrap it in many, many layers of bubble wrap and then drop it and hope for the best. But what we can do is back design the microlattice to absorb the force that the egg feels. So instead of having an egg that's wrapped in 3 feet of bubble wrap, now you have a much smaller package that your egg can sit in. One of the main applications that we've been looking into is structural components or aerospace. So when I get on an airplane and I'm leaning against the sidewall panel, I'm putting my luggage in the stow bin, or I'm walking along the floor panels, I think, the microlattice could be used in one of these applications. In the future, the material could help Boeing to save a lot of weight, make the airplanes more fuel efficient. It's really exciting to be able to work with things that we make that can eventually go into a real product that a lot of users can interact with.
Okay, so first of all, materials which are essentially void. 2 basic concepts for the previous video, then we will add something. And then with the example of the egg, materials which are able, if compared to bulk material, to store relevant quantity of energies even under impact conditions. These are two important points which characterize the cellular solids. So cellular solids are materials composed by cells, which are a region of bounded space, and which can be considered as an interconnection of linear here or planar, if you go inside the picture, elements, which forms respectively linear, that is lines which are going to be to converge in a point, they are called edges, or the planar elements, if you go through the slides, they are called also face. And the honeycomb is an example of a cellular solid, as well the foams are example of the cellular solids. What the young lady, the young scientist said, that is materials which are 99.9 void, with no mass, is said, technically speaking, looking to the relative density. This means, sorry for the Italian, but it's relative density, like this one, of the cellular solid, which is the ratio between the real density of the cellular solid and the density of the corresponding bulk materials. This ratio is in the range 0.3 to 0.001. That is, the density of the solid is very, very low. And what we are going to say, what we will say is referred to this case, that is to the case in which at least, if we want to use, let me say, a sort of target number, at least the relative density of the cellular solid is not higher than 0.1, most of time less of this. We can have two configuration of the cells. As the young lady also said, these kind of materials are found, apart from bone, in nature. For example, think to cork, think to sponges, think to balsa. So they aim to reproduce some already existing materials in nature. We can have two, let me say, limit situation. The case of in which cells are interconnected, that is the case in which cells are open, or the case in which cells are closed. And in this case, the faces are able to delimitate a region of space so that the inner of one cell is not in contact with the inner of another cell. Obviously, pay attention, we do not have void inside. We do not have mass, but the pressure is the atmospheric pressure. So we can have air, or in some cases, not so frequent, we can have some other gases, but the pressure inside is always equal to the atmospheric pressure. And then obviously we can have also the combination of open cells or closed cells, that is the mixed situation, and the possibility to fabricate or to have all open cells or closed cells has an impact to the mechanical behavior, that is to the mechanical properties of the cellular solids. This is these slides here is the case, this picture, sorry, of a nickel-based open cells. This is a polyethylene. This one is a polyester. That is the third, and the third picture refer to polymeric materials. The first one is referred to metallic materials. Honeycomb is a material which is very widely used in the aerospace fields. It can be as base materials, polymeric, metallic, or ceramic materials. The difference are the fabrication technologies according to the base materials of the honeycomb itself. So we can have, for example, multi-layer bonding or mold forming for polymeric based, mold forming for metallic, extrusion or mold forming for ceramics, as well as foams. They are also, let me say, very diffused in application. They belong to the fields of cellular solids, and they can be polymeric or metallic or ceramic with some difficulties. And also in this case, the fabrication technology can be different. If we look to this line for metallic solid state, you see here powder metallurgy is just the same concept that we taught before, that is the possibility to fabricate something which has holds a high level of porosity, like in this case. This is a very high level of porosity, and by controlling the sintering step during the power metallurgy based fabrication technology, and this can give rise also to some examples of cellular solids. Some general properties which can be considered with comparing to the corresponding bulk materials. When I say corresponding bulk materials, I'm again thinking to bulk materials being made by the same alloys of the cellular solid, but bulk, that is with relative density as it is, approaching the theoretical density. Obviously, being essentially without mass, they have high value of thermal insulation. This is important. And this high value of thermal insulation can be seen, for example, by looking to here to the bar of conductivity, which is very low, as well as we said, the density. If we remember that they are essentially void, so that the density you see here forms is very low, as well as high instead is the deformability, because very low are also the values of the Young modulus. These kind of materials also can be proposed to use not only for thermal insulation application, but also for packaging. And then having a low density, low conductivity, this can give rise to the possibility to use some combination of these materials for structural application. But for these, the most important feature will be the behavior in terms of energy absorption, as I mentioned to you before, which we will discuss later on. Now, to close the lessons of today, and next time we will go inside to this topic, just remember this, which is very important, that we can have being a non-varied decomposition, that is for the same composition, difference in two cellular solids with the same composition in cell size or in cell shape and distribution. Well, as general approach, as a general principle, cell shape and distribution, they do have a relevant effect on properties, less than the cell size, which has a low effect on properties. This means that when we want to fabricate cellular solids having, as it is desired for our application, a sort of homogeneous behavior, we must work on the cell shape and the cell's distribution and make it as more as possible homogeneous inside the materials itself, because these are the most important parameters which control the macroscopic properties of the materials itself, which we as engineer can measure and can define in terms of figures which are used for our design purpose. So I would say that for today it's enough, and we will continue this interesting topic, at least up to me, on the lessons of next Wednesday. If you have some questions, please do it. I'm here. No questions? Okay, if no questions arise, I greet you, and we will meet again in a couple of days. Have a good afternoon.